just ask, maybe you should move over to that side so that it's not an issue. I'm gonna just move the door a bit closer. Okay, so I'm gonna just go tilt a little bit. Okay. Mic check 1 2. Good morning, everybody. Ni right? Ni kwatile? Eh? Ankwatan? Okay, you don't look very friendly today. Your faces don't look friendly at all. Okay. Right, I just need to check in my and you go heavy with the lighting. Huh? Do you think that works better? And? Really? I don't know if that works. And I don't like the angle as well. Nope. The blinds are doing what? Are they what? Should I open them? Just a little. You think that makes a difference? Still doesn't make a difference. Isn't it too dark for you guys? Are you sure? Are you sure? Okay. Alright. Right, good morning, everybody. All right, to those of you that are joining us online, welcome. Thank you for joining us. We've got quite a number of people that are joining us from our online community. Mara, let's make sure that our own people here are also available. Some haven't joined in. Well, today we've got two very nice, pleasant surprises, right? Number one is that Tseho is back with us. Yay! Yeah, so good to see you, Tseho, after, that unfortunate incident that took place. But we receive you with such gratitude, and knowing fully well what our lives are in God's hands, ne? And this is round 2, right? Back in the days we used to play Street Fighter, right? And Nasa Street Fighter. Okay, so Nasa Street Fighter. At least there's one person who can relate. Yeah, so it goes round 1, fight. So she's on round 2. So we're saying fight, ne? Okay, awesome. So good to have you here. And we've got Usbonga Mahle is having her birthday namhlanje. So can you please sing for her? Happy birthday, dear Usbonga. Happy birthday to you. Yippee! Right. We really wish you all of God's best. Yeah. I know that growing up isn't easy. Life gets challenging. Yeah. But I pray that God blesses you, keeps you. Okay. May He make His face shine upon you. Ne? Yeah. Yeah. All right. Hopefully, she'll get us cake. No pressure. Okay. So for those of you that are joining us from our YouTube community, please do note, I think there was an error in announcement that we're doing financial maths. Today we will be covering probability. All right. Hopefully we can do that another time, covering financial maths. Nonetheless, we will be starting with the lesson. And good morning to those of you that are joining us online, even though Anpelelanga is yet. Right. So we're going to start in a few. So I thought namhlanje in introducing the section, and that's why I went live today instead of going live tomorrow. So I wanted us to really look at a couple of things. One of the couple of things that we need to look for is that I don't have my pen here. Okay, commercial break. All right. So, first of all, let me just say categorically that probability is really not a difficult section, right? Why are you saying woo? Okay. Right. Hopefully by the end of this lesson or by the end of these sessions, you will agree with me that it's not a difficult section. Né? Right. Now, can I just say a couple of things? So I'm going to focus a little bit on Venn diagrams today. Né? But firstly, I'd like for us to talk. So what is probability? This is the chance of something, an event taking place, right? So I'll make an example. In this case, if I look at the probability of getting an even number when I throw a die, right? Okay? So what are the chances of me getting an even number? Well, it is the probability is on the number of even numbers that I have divided by the total number of outcomes that are possible. Does that make sense? Ne? So if you think about a die, right, how many numbers are there? We've got 6 possibilities, isn't it? Right? But how many even numbers are there? We've got only 3, right? That would be 2, that's 4, and that's 6. Okay, so those are the even numbers. So, which means if I look at the probability of an event taking place, right, that would be, in this case, the number of possible outcomes. So this would be possible outcomes, or rather, let me say, the number of events that are possible, right, divided by the number of possible outcomes. Okay. Right, so that would be the number of possible outcomes that are possible. No? Right, and I did make an example. I said, well, in that case, how many of them are there? So that would be 3, and when I talk about even numbers, but the total number of outcomes that are possible in this case would be 6. Okay, so the chance of you getting an even number when you throw a die is 0.5. Now, I want you to note there are 3 ways in which we represent probabilities, right? The first one is we can represent it as a fraction. Right, and when we represent it as a fraction, in this case, that fraction must be a proper fraction. Now, do we know what a proper fraction is? The denominator is always bigger than the numerator, right? Okay, so in that case, you can have 3 over 10. That's a proper fraction, okay? We've got a denominator that is bigger than the numerator. Another way that we can represent the probability is through a percentage. We can represent it as a percentage, and all we need to do is we take that fraction and we multiply by 100, and it represents the probability as a percentage. Okay, so usually we watch the weather forecast, right, when they are telling us about the possibilities of rain. Okay, you know, back in the days I used to think when they say 70%, they mean that it's going to rain by 70%. I don't know what 70% is. Like, that's how hard it's raining, you know. In that case, when we talk about a percentage, we're talking about, remember, a percentage is always out of 100, right? So you can say that, what is the chance that, I don't know, let's take the issue of throwing a dice again. So that means, in that case, the possibility of getting an even number is 50%. And because what did we do? We said, well, that's going to be 3 over 6. That's multiplied by 100. And so you'll realize that gives us 50%. So we can represent a probability as a fraction. We can represent it as a percentage. And the last one is we can represent it as a decimal. Right? So we can represent it as a decimal. Now meaning, right, I'm going to switch this thing off. Right, so meaning that if I represent it as a decimal, it must be a number that is less than 1. Okay? Right? So it must always be a number that is less than 1. So meaning that I can represent this probability of getting an even number from a die as just 3 divided by 6, which is 0.5. So I can say this is 0.5. Are we all okay, guys? No? It's sharp. All right. Now, one of the rules that we are going to use is what we refer to as the complementary rule. All right. The complementary rule simply says the probability of an event not happening will be equals to 1 minus the probability of an event. Okay? So let me make an example. Okay? So if I say to you, what are the chances that it might rain today? If the chance is 20%, remember I said to you we can represent this as a percentage, we can represent this as a fraction, isn't it? So as a fraction, what would it be? This would either be 20 over 100, or you can say this is 2 over 10. Those are the chances of it raining, right? But now, if I say to you the chances that it might rain today is 20%, what's the chance that it might not rain? 80%. Now, how do we get that? That's the complementary rule, right? Because we're saying the event or the chances that the event might not take place would be 1 minus the percentage that we've got, which was 0.2, and so you get 0.8 if I represent it as a decimal. Are we together, guys? Nah? Right? Miss, I say right? Yes. Does it make sense? Yes. Okay. All right. So we call it the complementary rule. In particular, you will see this on events, especially when we use tree diagrams, right? So for instance, if I said to you, we've got 3 balls, 3 red and 1 blue, okay? What is the chance that we might pick a red ball? The chance of picking a red ball, probability of red. So the probability of taking a red ball would be 3 out of how many? Out of 4, right? So the probability of picking a blue ball, or we can say the probability of not red. Do you see that, no? So what would be the probability of not red? Well, you can read it off from what we have. We've got 1 blue ball out of 4, right? So, but you can also say, but this is actually 1 minus the probability of picking red. So if I say to you, the probability of picking blue, this would be 1 minus the probability of picking a red ball. That's using the complementary rule. Does this make sense, guys? Ne? And you'll realize if I say 1 minus 3 over 4, you'll realize that you'll also get 1 over 4. This we call the complementary rule. Now, why is this important? For this mere example that I just gave you, they'll say to you, Untombi Zodwa, I don't know why I just thought of that name. Okay, Untombi Zodwa, has got, no, actually, maybe let's use the one of the rain, right? The chances that it might rain on a particular day, on a Tuesday, is 30%. But what they don't tell you is the chances that it might not rain, right? So you need to then use the complementary rule in that regard. Okay, right. I am rushing as much as I possibly can. Please, if there are any questions, let me know. Right. The second thing that we want to look at in terms of probability is what we refer to as mutual exclusivity. And I'm going to make examples. If I say to you, events are mutually exclusive, right? Well, it simply means that those two events can never have what we call an intersection, would never intersect. So if you think of it as a Venn diagram, okay? So these are two possible events that we've got. So let's say we've got a number of students that are here in class. Some of them are doing maths. Some of them are doing science. Okay, I'm just going to refer, or rather use S there, right? Now, and this is a very good example using us here in class, né? Okay? So let's say 30 of you, and there's 30 of you in the class. And, sorry, now, let's say 25 out of the 30 are doing maths. Okay? And let's say 20 out of those are doing science. So do you agree with me that 25 plus 20 will not give us 30? What does it mean in that case? Say that again. Some of them are doing both. So you must be careful when we say to you maths only. So if we don't say that, it means that there is a possibility that if I say to you the probability of picking a random student and find that they're doing maths, right? So then it means that it might also include those that are doing maths and science. Does that make sense? No? It doesn't exclude the ones that are doing both maths and science. So in this case, what I want us to quickly have a look at. So if I say to you events are mutually exclusive. Now, in any school that you go to, right, is there a possibility of finding a student that does both maths and maths literacy?
Yes.
Huh? Maths and maths literacy?
Yes.
It is possible?
Yes.
Really?
Yes.
Why? Because they are written on the same day?
No, it's on the same day.
Okay. Okay.
Because,
All right. Maybe in IEP there's...
yeah, because they write math, lit, and science one day, and then they write math on another day.
Is it?
Yes.
Okay.
So there are kids that do math and math.
You see, now you've ruined my...
Sorry.
You've ruined my... Okay. Excluding in IEP schools. Okay. All right. Let's say in a GDE school, right? Is there a possibility of getting a learner that does maths and maths literacy? No, it's not possible because it's written on the same day. So it's either you are doing maths or you are doing, well, let me call it maths, pure maths, right? It's either you're doing pure maths or you're doing maths literacy. Does that make sense? Now, what can I therefore conclude? It means that the events doing maths and the event doing mathematical literacy are then said to be mutually exclusive. Does that make sense, guys? What does that mean? They can never intersect. There could never be a possibility of finding a student that does both math and mathematical literacy. Does that make sense, guys? Right. Now, how does that affect us? So we say the probability of doing math, okay, let's call it pure math, PM and ML, right? So the probability of finding a student that does pure maths, we called it PM, and we usually use this symbol U, right, for the union between the two, right? Or we can just simply write and mathematical literacy, right? So the probability of that is what? 0. Does that make sense, guys? Please, I want you to keep this in mind. The moment we say that events are mutually exclusive, what it simply means is that those two events, the probability of A and B is essentially 0. There is no, there's no intersection between the two. Okay, I'll come back to this a little bit later when I talk about the equation that we use, the general equation for probability. Okay, right. Does this make sense, guys? I really want it to make sense, yes? Our online people, see right?
Yes, sir.
All right, beautiful stuff. Does this make sense, guys? So keep that in mind. If I say to you I've got two events that are A and B, and I say to you those events are mutually exclusive, please don't forget this. So it means that the probability of A and B is going to be equal to 0. Okay, right. As I said, I'm going to come back to this when I do the general principle of probability. Now, when we talk about probability of, so let's say this is our sample space. When we talk about a sample space, we are simply talking about the total population size. I made an example about our class, ne? I said, okay, suppose that we've got students that are doing maths, but we also have those that are doing science, but we also have those that are doing both maths and science, right? So if we said, okay, the number of those that are doing only maths, right, would be, maybe that's a smaller number, ne? Okay, let's say 5. And let's say those that are doing only science, let's say that would be 10. Now out of 30, how many are doing both maths and science? If that were the case. How many are doing both maths and science? That would be 15, isn't it? Right. Now, if I say to you, now I want to use a word. If I say to you, we've got an exhaustive sample space. Right. What does that mean when I say to you it's an exhaustive sample space? Well, let's take an example with here in class. Everyone is either doing maths or science. Do you guys agree with me? No? Of course we have to agree. Okay. Everyone is doing maths or science, right? Is there any students that does neither maths nor science? No. So then what can I say? It means all of my population falls within my elements. Are you guys with me now? Right? So which means there's nothing that falls outside, and I'm going to now use a specific word in this case. There's nothing that falls outside of our circles, right? So we therefore say that the sample space is exhaustive. Why? Because the probability of finding a student that does maths or science, what is it? It's It's 100%. It's either you are doing maths, or you are doing science, or you are doing both. There's no student that doesn't do either one of them. Does that make sense, guys? Okay? Blessing, you look lost. We are here, yeah? Okay, right. Right, so there's no student that doesn't do either one of those two subjects. Now, what I'm just simply trying to say, when we draw our Venn diagram and we find Uti, there's nothing outside, okay, of our sets. We call them sets, ne? There's nothing outside of those sets. Then we say that that sample space is exhaustive. Are you guys with me, ne? It means all of your population falls within your sets. Now, let's just say for argument's sake, let me make an example. If I say to you, the students that are enrolled at the center, some of them do maths, or rather, some of them have done English, and some of them have done geography. Right? Did everyone do geography? Okay? Right. Is it possible? In fact, now let me not use. Let me say rather. Let's use geography and life science. Yes. Life science. Okay. So some of you have done life sciences. Some of you have done geography, right? Are there people who've done both? Yes. All right. So, which means. Is the other events, life science and geography, mutually exclusive? In that case, for the students, for the population that's here, they're not mutually exclusive, right? Why? Because there are some who would fall here. I have done both life science as well as geography. Okay? Is there anyone who has done neither life science nor geography? Okay, so we do have people that fall within that. So, would this be an exhaustive sample space? No, it's not, right? Why? Because there will be people, even though by two, but oksalayo, they are there, right? So, which means the probability of life science, of getting a random student that has done life science or geography is not equal to 1. Okay? So what am I saying? It's not 100% of the students that are here that have done life science or geography. As we've just discovered right now, there are those that have not done either geography or life sciences. So it is not an exhaustive sample space in that case. Does that make sense, guys? Right. And I really want you guys to understand these words. It's just fancy words for nothing. Ne? Right. Now, let's talk about another word that we normally use in probability. The word independent. When we say that events are independent, right? Meaning, the first outcome is dependent on what happens, the second outcome depends on what happens on the first outcome. Now, let me just make an example. If I were to flip a coin, right? Imagine I'm flipping a coin and then it lands on the palm of my hand, right? So let's say we get an outcome. Sitting. Head or tail? Heads, right? Okay, head. We get an outcome, and the outcome is heads, right? Now, my question is, when I flip it for the second time, is the outcome going to be dependent on what happened the first time around? No, right? Okay, so that outcome is not dependent on what happened the first time. So in that case, those would be independent events. Now, please, I want you to listen very carefully, right? When we have independent events, we say that the probability of A and B, so meaning the one and the other. So in that case, the first outcome and the second outcome, right? This will be equal to the probability of A multiplied by the probability of B. Now you will see in the questions that we're going to do, some of them that say to you, prove that the events what? The events choosing a subject or a career and the choice of subject. Yeah, choosing a career and choice of subject are independent. So what do? You're going to go into whatever sample space that you've got. Either they would have given you a contingency diagram, or either they would have given you a Venn diagram, right? So let's go back to the one that we had. The events, choosing maths and science, right? Are they independent events? So we are going to go and say the probability of A and B, the probability of maths and science, right? Is it going to be equal to the probability of maths only multiplied by the probability of science only? Does that make sense? Né? Right. If we find that those two are actually equal, then we know that those events are independent. Is it a lot of information, guys? Is it a lot of information? But ningawari, we'll get into it just now, and you will understand it as we go on, as we go ahead. Right? Now, I've given you two very important events around probability of something and something else. The one was around mutual exclusivity, right? I said probability of A and B is equal to 0. Independence, the probability of A and B is equal to the probability of A multiplied by the probability of B. Are we all together, guys? All right. Now let's talk about just a few things when we are looking at our diagrams. Ne? Trying to remove this guy. So let's say that we've got a sample space over here. And we've got two events, A and B. So if I say to you the probability of A, where do I take that? Right? Which means I'm going to take everything that falls under set A. Does that make sense, guys? Right. So, if this was maths and science, if I set the probability of choosing a random student and finding that they do maths, right? Which means that I'm going to take everything under the set A, including those that are doing both maths and science. Are you guys with me? Right. Now, if I said to you, the probability of B, note again, very same thing. What am I going to do? If you don't mind, I'm going to just remove this. So that means I'm taking everything that is under B. Okay? Now, if I say to you, on the other hand, the probability of A and B. I've already shown you that one. Eh? Where do we get that? We said this is the intersection between the two. Okay? So that's the probability of A and B from a visual perspective. Now, if I say to you the probability, let me take another one. if I say to you the probability of A only, or the probability of only A, where do I get that? That would be only A. All right? And if I say to you the probability of A or B, right? If I said to you the probability of finding a random student and find that they are doing maths or science, right? So what do? We're going to take everything under both our sets. Does this make sense, guys? Right, so the probability of A or B. Right, it's going to get lively just now because I want us to get into that. Okay. Right, are we all okay so far, guys? Nisho. All right, beautiful stuff. And of course, there's the probability of not A, right? If I said to you the probability of not A or B, so we usually just use a prime for not, so which means this would be anything else that is outside of our sample space. Okay, not our sample space rather, but outside of our sets. Okay. Sisase right on it, guys. All right. So here's what I want us to do today. Né? I'm going to give you this formula. And this formula, we always use it on probability. You'll see it. It's going to feature quite a lot, especially when we do those random questions. And the formula, the general formula of probability simply says the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. The reason why I like this formula né, is that if I give you different conditions, so for instance, if I said to you A and B are mutually exclusive, right, what do we know about mutual exclusivity? What did we say? Yes? Events can't happen at the same time in terms of probability. The probability of A and B is 0. Does that make sense? So once I give you that condition, when you have to use this formula, then what does it mean? It means that I can use my general formula and say the probability of A or B is probability of A plus the probability of B minus what's the probability of A and B? 0. So which means for mutual exclusivity, the probability of A or B will simply be equal to the probability of A plus the probability of B. You don't need to remember this. All we need is this formula here and to know how to apply our conditions. Does that make sense? Right. If I said to you the events are independent, right? How does that change our formula? Again, probability of A or B equals to probability of A plus probability of B minus what's the probability of A and B if I've got independent events? Probability of A multiplied by probability of B. Again, you do not need to memorize what I've just said, right? You just need to know what it means in terms of those conditions. Happy days? All right. Okay, I said we're going to do some practical examples. I see Kia is feeling nervous. I see... Me right? Okay. Right. Does this make sense? Or is it a probability and then never scan? You are ready for action, eh? Hungry for blood. All right, let's get into it. So what I want us to do is to, firstly, I want us to kind of learn how to interpret Venn diagrams. And very deliberately, I'm starting you guys with ones that have 3 sets. I'm going to ask a couple of questions right now. Nah? Firstly, is this an exhaustive sample space? Why not? Aha, we've got the 27 that are not included, right, in our set. So which means whatever there is going on in those sets, those 27 are not involved. Does that make sense? So meaning the probability of C or F or W is not equal to 1. That's not 100% of our population that falls within those elements. Okay? Right. Now they say to us, a school organized a dance for 150 grade 12 learners, right? The learners were asked to indicate their preference for the theme. They had to choose from casino, France, and winter. So those are the themes that they chose, né? Right. In France and winter wonderland. Okay, I was wondering, what's the 4th one doing? Right, the information collected is shown in the Venn diagram below. All right. So we've got learners that chose a casino theme. We've got learners that chose France, the France theme. And we've got learners that chose winter wonderland. Now they say to us, calculate the probability that a learner chosen at random does not prefer casino or France. So, which means if they don't prefer casino or France, what do they prefer? Winter wonderland only, or they don't prefer any of the 3 themes. Does that make sense? Right. So which means it's anyone outside of the elements casino and France. So meaning that they shouldn't be here, they shouldn't be here, right? And in that case, it means they should be only choosing winter wonderland or choosing nothing at all. Does that make sense? Right. So how are we going to determine that probability? So for 3.1.1, so the probability of, we said not casino or France, ne? Right, casino of France, but we're saying not casino of France. In that case, would be, you don't even need to be fancy about it. So that's going to be 21. Okay, sorry, can I just remove this so that it doesn't disturb? It's the 21 plus the 27 divided by how many students? Right, they told us we've got a total sample size of 150. Does it make sense, guys? You sure? Okay. Right. So let's find another probability. Okay, so we can represent this, as I said to you, as a fraction. So 21 plus 27, my calculator says 0.32. Is that true? Okay. So, meaning that if we wanted to represent this as a percentage, what would we do? Multiply this by 100. Okay? So it would be 32% of the students actually do not prefer Casino or France. Right, let's go to the next one. 3.1.2. They say calculate the probability that a learner chosen at random prefers only 2 of the given theme choices. Only 2. Now, let's check. How many of them preferred only 2 of the choices? So do you agree with me? These ones chose 3. Right? So which means they are saying, whatever, man. Whatever goes, right? These ones only chose 1. Right? And the other ones chose absolutely nothing. So which means the ones that chose only 2, which ones are those? That's 11 plus 8 as well as the 4. So the probability of choosing only 2 events, we're going to say that's 4 plus 8 plus 11 divided by 150. Please tell us. That's 0.153, or you can say 0.15, nah? Okay. Are we all good, guys? Right. Now, the last question from those says, show with all working whether the events preferring Casino and preferring France are independent or not. Now, there's that thing, independence coming in, right? So what do we need to prove? So whenever we are proving independence, we said, if they're independent, what would happen? It means the probability of choosing Casino and France should be equal to the probability of Casino multiplied by the probability of France. Make sense, guys, no? All right. So please, let's try and find that out. So what's the probability of choosing Casino and France? Where is that? Do you guys agree? That intersection there, no? Right. Now you can say, well, but the 15 chose all 3 of them, but it doesn't exclude the fact, Yoguti, they chose Casino and France. Does that make sense? Right? They didn't exclusively say Casino and France only, right? So in that case, it's the 4 plus the 15. So I'm going to say the probability, okay, let me do this. Let me do this. So I'm going to separate them. The probability of Casino and France. So we said that's going to be the 4 plus the 15 divided by 150, nah? That gives us 0. Should we round it off to 0.13? Okay, 0.13. Now let's do this. Let's take the probability of Casino, of choosing Casino, multiplied by the probability of choosing France. So let's go to our elements. Which ones chose Casino? So remember I said to you, which means it's everything under this set here. Are you guys with me? Right, so let's add them up. So that's 23 plus 8 plus 4 plus 15. What's that? Okay, maybe let me do this. So we said 23 plus 8 plus 4 plus 15, né? Divided by 150. So these ones are the casino people. Multiplied by the probability of choosing France. So which ones are the France people? Which ones are the France people? Right, so that's 4, that's 15, that's 41 and 11. It's 4, that's 15. So you take 41, ne? Is it 41? Yes, 41 and 11. Over 150. All right, so please find out for me. Sorry that I squeezed myself into a corner there. 0.16. So we get 0.16 as our final answer. What is my conclusion therefore? They are not independent, right? If they were independent, it means that the probability of casino in France would be equal to the probability of casino multiplied by the probability of France. Ne? Okay, sorry, I just wanted to write this one properly. We had said that's 23, 4, 15, and 8. This is over 150. And we said this is 41, 15, 11, and 4. This is divided by 150. All right, and you've got 0.16. Now we can therefore conclude that the events, the events choosing or preferring casino, I'm just going to summarize it. The events casino and France are not independent. Okay? The reason for that is that the probability of casino and France is not equal to the probability of casino multiplied by probability of France. Is it right, guys? Is probability still very bad? Still very good? Okay, right. Should we take another example?
Yes.
Okay. Were you guys able to write everything? Okay, don't worry, I'll send you all of these questions. Right. Yeah, gradually, siyasondela, ne? I want you in the next few minutes, we're going to be drawing our own Venn diagram, right? Those are the questions that sometimes give us a little bit of an issue. Right, now they are saying to us there are 115 people in a group. The Venn diagram below shows the number of people who enjoy listening to radio, enjoy gardening, and enjoy cooking. Right. Anyone who enjoys cooking here in class? You enjoy it? You know how to do it? Yeah. Why not call? You guys, Nina. Nina. and then charge. Okay, right. So, anyone enjoys gardening? Gardening. Okay. Would you consider being a farmer? Probably, no? Okay. Because that's like one big garden, right? It's just the difference. Okay. Anyone who enjoys listening to radio? You guys hardly listen to radio. TikTok radio, you know? Okay. All right. So they say to us we've got 115. So you mustn't forget that. Né? So usually when you're doing these kind of examples, when we are given, a sample space and we've got table X and Y's that are happening, please don't forget the total population size is usually given. Né? Right. Now they say to us, if there are 28 people who enjoy gardening, calculate the value of X. So my question is, how would we get the value of X given this? Right? So in a sense, let's first look at this. What is X? X is the number of people that enjoy all three, right? They enjoy cooking, gardening, as well as listening to radio. I think there's a correlation there between the three. I mean, if you enjoy gardening, you plant the stuff, right? And you cook the stuff that you planted. And whilst you cook, you're listening to radio. Yeah, so there's a... okay, so it makes sense. I think the ones that make sense for me are all these. Lavabanya. I'm not sure. Right. I enjoy listening to podcasts usually when I cook. Okay. So they say if there are 28 people who enjoy gardening, calculate the value of X. All right. So which ones enjoy gardening? It's all of these people here, right? So then in that case, in order for us to calculate the value of X, what are we going to do? We take everything that is under gardening, so that means that 7 plus X plus 10 plus 3, and what should that give us? 28, right? And so, what should be the value of X? So that's 8. So that should be 28 minus 20. If we add all of these up together, they give us 20. So that means that X is equal to 8. So 8 people enjoy listening to all three, or rather doing all three activities. Right, and then they say hence determine the value of Y. How would we get the value of Y? Now Y here. How would I get the value of Y? Yes?
So we calculated the value of events. So the number we put into X is in all the events.
In all the sets, right? Okay.
After we add them together, we subtract the number for total people.
Right, so please don't forget that. Beautiful stuff. So, we're now taking, we remember the total sample space here too is 115 people. But now that we know what X is, right, we can substitute for X for all of the numbers that we've got there, all right? But we know that that should give us, if you don't mind, I'm just going to, we remember to X is 8, right? Okay, so I want my diagram to be just in front of me. So you can say, which means 47 minus X plus 7 plus X plus 2 plus 20 minus X. You need to be very meticulous here, né? So that you don't count the same thing twice. Plus 20 minus X plus 10. Angamcounti, ne? Plus 3 plus y, that's equal to 115. So that's our total population size. Okay? So let's see, minus x and x cancel out. And I've got, yeah, so you can add everything up, but we know that x is equal to 8. So we can substitute that. Please tell me what the value of y is. That's 18. Okay. What did you get? 34. 34, okay. 34. 34. Online, I hope you got 34 as well. So we find that the value is 34. Right. Now, may I ask you to do something for me? I'm just giving you a random question. Né? Calculate the probability that any person selected at random loves cooking and gardening. Any person that is selected at random loves cooking and gardening. How many? So who are the cooking and gardening people? They should be here, right? We know X is 8. And we know that we've got 10 there. So that should be 18 over 150. Are you guys with me now? Right. And then if I said to you, if I chose any person at random that loves, no, actually, that does not prefer listening to radio. Does not like radio at all. Right, for those of you that are watching on our YouTube, please just hoy on the comments there so that we can see what your answers are. This is on Jajalash. I'm kidding. Huh? The 18? The 18 over 150. And those ones were the cookists and gardeners, so we took them here.
So it's out of 115.
Excuse me?
It's over 115.
115. Sorry, I said 150. Apologies there.
So was it the probability of CNG only?
So I said the probability that any person selected at random loves cooking and gardening, right? So in that case, you would have to take the intersection between the two, right? But if I said cooking or gardening, I think that's what you were thinking about right now, ne? Okay, right. Yeah? About Tanda who do not prefer listening to radio. That's what I said, ne?
Yes.
Okay. How many? 59.
Over 150.
59 over 150. Okay? So who were those who did not prefer listening to radio? So which means anyone You agree with me that all of these, including these ones that are outside, please don't forget about that, né? Right? So, the 3, the 10, these ones love cooking, these ones love cooking and gardening, these ones love gardening. So all of those don't like listening to radio. So meaning we're taking everything that does not have fellowship with this guy over here. Are you guys with me now? Right. Anything that does not fall into that, but please don't forget that we need to also include the people that do not listen or do not prefer any of those events. Does that make sense, guys? All right, beautiful stuff. Okay, so here's what I want us to do, manje. Right now that you know what to do. Says Jimmy, Lena. Anna says Jimmy. Okay, says Jimmy. Okay, right. I want us to quickly have a look at how do we now construct a Venn diagram given information. Right? I want to do one example with you and then you're going to do the next one. Huh? Do you promise? Okay. So they say to us we've got most of grade 11s of Freedom School. Make use of public transport. The 3 available modes of public transport are buses, minibus taxis, and trains. Right, but there are 100 grade 11 learners in the school, so please remember that's our sample space, isn't it? Right, they say, right, of whom 29 use buses, 62 use minibus taxis, and 40 use trains. Is that information usable if we were to construct a Venn diagram? Well, no, we can't. Ne? So we can't use that information. Why? Can anyone tell me why we can't use that information? Why can I not use this? That first set of information. Because for the one that uses buses, I don't know whether they use a bus and a minibus taxi. They didn't say use buses only. Are you with me now? So you must be very careful when you are going to construct a Venn diagram, that the information that you are taking specifically says something about that particular space, right? So let's do this. I'm going to try and construct them, and let's make it as big as possible. So these are buses, minibus taxis, and trains. The problem is that yeah. Hey man, this guy is showing me flames today. Okay, let's try and make our circle. Okay, right, so there we are. So these are trains. So let's try and look at the next set of information. So with these kind of examples, guys, and please, I want you to be very mindful of this. You always start where you've got the most specific information. Okay? Right, so when you're not sure, just leave it. Okay? Right, so we've got those buses, trains, and minibus taxis, and they say 12 use buses and minibus taxis. Is that specific information? Is that very specific? Okay? So, perhaps we could say, well, at least it's getting better. They're telling us about the 12 that use that use buses and minibus taxis. But we don't know if maybe there's one or two that also use trains. I know they use both. Maybe they use all three. Do you see that, no? Right? Okay, they say 22 use buses and trains. Okay? Again, we'll come back to it. And they say to us 17 use minibus taxis and trains. They say 13 don't use public transport. Okay, at least I know what to do with that one. Okay? So firstly, I'm going to start with the 13 in my case. Right? I want to start with the 13 because that's very specific. Now they say to us, let the learners let the number of learners who use all three modes of transport be X. Now that can be helpful. So meaning this is going to be X. Are you guys with me now? Right. Now stay with me. Nisasenam. Okay. So we're going to go back into the information and let's see how we can try and fill this in as much as we possibly can. They said 17 use minibus taxis and trains. 17 minibus taxis and trains. Where is that? Minibus taxis and trains. Right? How many are those? 17. Now, which means, what would be this value here? 17 minus x. So that 17 minus x plus that x would give me 17. Do you remember I said to you, they did say minibus taxis and trains, but they did not necessarily say exclusively. Are you guys with me? Right? But I know that the number of learners that are using minibus taxis and trains are 17, so which means we are also including the learners that are using all three. Make sense? Okay. Is it getting better? Okay. Then let's go back. 22 use buses and trains. Okay, so let's go to buses and trains. Where is that? That's over here. Right? How many are using buses and trains? 22. So which means, how many would be here? 22 minus x. Okay? Right, let's go to the next set of information. They said 12 use buses and minibus taxis. You know the drill, Marjane, right? So which means over here, sorry, I don't have as much space. That's 12 minus x. Okay, right, I hope that it does make sense to all of us. All right, now let's try and fill in the rest of the information. So this is where we can now include everything. They said to us, 29 use buses. So remember, the 29 that use buses, they didn't say to us 29 use buses only, right? Which means we are including those that are using buses and taxis, buses and trains, buses, and buses only. Does that make sense? Right, so how many are using buses only in that case? Then you can say, which means whatever this is, what do you want to call it? Buses only, B, right? Plus 12 minus x plus x plus 22 minus x. How many should they be in total? there should be 29. In total, we should get 29 of those that are using buses. So in that case, what are we going to say? Well, minus x and x cancel out, right? So what would be the value of b? B would be equal to 29. This is 12 plus 22, which would give us 34, no? Is it 34? Okay. So this is, if we take x to the other side. So we're going to find 29 minus 34 plus x. What is that equal to? X minus 5. Does it make sense? All right. So which means over there we are going to have x minus 5. My online people, yazni tulile today. Are you guys still okay?
Yes, sir.
All right. Please, if there's anything that you don't understand, please let me know. Nah? Right. So let's go to the next question. So they say to us, or rather the next one, the next set. So the next set, they said 62 use minibus taxis. So which means for minibus taxis, or minibus taxis only, plus 12 minus x, plus x, plus 17 minus x, this is equal to 62, nah? Again, this and this cancel. What would be the value of m? We've got 12 plus x, plus 17, which gives us 29. Okay, minus that 62 on the other side. So m would be 62 minus 29 plus x. What does that give us? 33 plus x. I hope this is helpful, guys. And then the last one that we had were the 40 that were using the train. Okay? So the ones that are using the train, we're going to say 22 minus x plus 17 minus x plus, we'll call it t. Nah? So I'll say t plus 22 minus x plus the x plus the 17 minus x. Okay. Right, what does that give us, Konje? 40, nah? That's equal to 40. Again, we're going to cancel this guy and that. So what should be the value of t? We've got 22 plus 17, that gives us 29. So I've got 40 minus 29. 39 rather. That's 40 minus 39 plus x. So what do we have here? 1 plus x. So which means over here we've got 1 plus x. All right, so there we have it, guys. Our very first question. Remember, how many learners, grade 11 learners did we have? We've got 100, yeah? Our very first question says we should draw the Venn diagrams, which we've just done right now. And please solve for x for me. How are we going to get x? How are we going to get x? All right? So which means we're going to add everything under our sample space, right? Meaning x minus 5 plus 12 minus x, plus 33 plus x, plus x, plus 22 minus x, plus 17 minus x, plus 1, plus 13. What must it give us? It must give us 100. Okay, and that will give us the value of x. Ngathi yanwarisha nje, Lauren? Okay. Right, I hope that it does make sense. I wanted to squeeze one last question. Maybe we can. Nah? Should we? Should we? Oh, wait. One last one. When you find something, let me know. If you don't mind, I'm just going to erase this so that I've got more space. I'm trying not to move away from our diagram. So, we said we're going to take x minus 5 plus 12 minus x plus 33 plus x. This is plus 22 minus x plus x plus 17 minus x plus 1 plus x plus 13. And please don't forget the 13. And this is equal to 100. Okay, I've got x and minus x here. I've got another x and minus x there. I've got another x and minus x there, right? And then we add everything else. Minus, okay, that's minus 5 plus 12 plus 33 plus 22 plus 17 plus 1 plus 13. Aibo, what's happening, man? Or did I multiply?
Yeah.
17 plus 1 plus 1 plus 13. Okay. Right, and I get 100 minus 93, and I get x is equal to 7. Did you all get the same? Beautiful, beautiful. So we know that x is equal to 7. Eh? Right, now, here's what I'd like for you to do. Please answer question C, 1, 2, and 3. They say, a grade 11 learner is chosen at random, right? Determine the probability that the learner uses buses and minibus taxis, but not trains. It's very specific, right? Uses bus minibus, taxis, but not trains. Okay. Uzogcina ngayo. Which are the ones that are using buses?
Yeah.
And minibus, but not trains. Now we are buses. We are focused. I agree. So on the first one, I wanted to find out. So when they said to us, we are just taking learners that are using buses and minibus taxis, right? But not trains. I see a lot of you interpreted that as all. Right? So, they said, what happens when I say and? Right, which means I am looking for an intersection of bus and minibus, but they are not taking trains. Because if we had just said bus and minibus, then it means it would have also included the X as well. Does that make sense? Right? But we said specifically. So you've got different groups of learners. You've got ones that are using exclusively buses, just buses, right? Which is the X minus 5. Of course, we now know what X is, right? So it means it's 2 learners. We've got the ones that are using minibus taxis, which are the 33 plus X, right? Which is 40, right? And then we've got the ones that are using just buses, they're using, both modes of transport, which is the 12 minus X. So in actual fact, when you're looking at answering question 1, that's the one we're looking for. Okay. Does it make sense, guys? So please, I want you guys to understand the language of probability. Okay? the condition there, that would have been buses or I think it's a very good question that Uzema is asking. Sorry, we can. Yes, I want to say that we. Now I'm confusing the two of you again. That we guy is asking is then what would have been the question for us to use B, lega B, M, and the one in between? That would have been, what's the probability of a learner using either buses or minibus taxis? Because then it includes all of that. Does that make sense? Eh? Right. Please, I want us to keep that in mind whenever we look at those questions. Right. So what I was saying there is for the first one, we are only exclusively going to look at these ones over here. Right? Those ones are using strictly buses and minibus taxis, but not trains. So the probability of bus, and minibus only, right? So we said, what is it? It's a 12 minus x, right? But we know what what x is. So that would be 12 minus x, which is 7. But this is out of how many learners, Gonje? 100. That's 100. Okay, so 12 minus 7, that would give us 0.05. You can still express this as a percentage, but asiko lapo. Right, the second one, learner that uses only one mode of transport, okay, of public transport. So which ones are those? Abo exclusive labone. So which ones? That's the x minus 5. That's the 33 plus x. That's the x plus 1. Good? All right, so we add all of those up. So probability of only one. So 7 minus 5, that's 2 plus 8, that's x plus 1. And then the other ones, that's 40. And this is divided by 100. Okay, so that would be, yeah, 40 plus 8 plus 2, that's 15, eh? So that means that's 0.5. I wonder what did this thing smoke? Okay. They say a person uses more than one mode of transport, okay? One mode of public transport. Okay, right. So which ones are using more than one? So it's definitely going to be these ones over here, these ones there, these ones there, and those ones over there, nah? Okay, so we're going to add all of those up. So this is going to be 12 minus x, which is 5, right? Plus 7, plus 10, plus 15. Is it a probability of what? More than one. So you said, what was your final answer? 0.37. Okay, guys, let's leave it there. Okay, I'll give you guys some more examples next time. I think I was trying to squeeze in one last one, but I hope this was helpful. No? Was it helpful? Yes. Sure. Okay. All right. For those of you that are online, right, we'll meet for physics in the next few minutes. Was it helpful to all of you guys? This good is nice. All right, and that goes also for those of you that are joining us on our channel. Please note that we will be coming back again tomorrow for physical science. We'll be looking at acids and bases. It's been a pleasure being with you. Join us again next time. Sharp.
This one.